In this video, I want to introduce another important second-order circuit, the bandpass filter. That's one in which the gain is very low at very low frequencies and at very high frequencies, but has a significant amount of gain around frequencies in the middle. For example, consider this circuit. We can analyse its frequency response using the potential divider equation in exactly the same way that we've done many times before. And in this case, that would just give R over R plus j omega L plus 1 over j omega C, and multiplying through by j omega C to get the numerator and the denominator in the form of polynomials in j omega reveals this expression here. We can see that we've now got a single zero at 0 Hertz. So if we were going to plot the amplitude response, in this case, we would expect the gain to be increasing at 20 dBs per decade from low frequencies up until the break point of the first pole, and then it would level off, and then when we get to the break point of the second pole, it would head back down at 20 dBs per decade, and we'd get a frequency response something like this. The useful things to know about these bandpass filters is, firstly, what is the maximum gain? And secondly, what is the 3 dB bandwidth? So if you're 3 dB down on the maximum gain, what is this range of frequencies here? And it turns out that the answer to both of these questions is a very simple formula, although they do take a bit of deriving. There are a couple of tricks and shortcuts in the derivations, so I'll show you the easy way. First of all, let's make our derivation a bit more generic, and we'll do it in terms of the resonant frequency and the Q factor rather than the values of resistors and inductors and capacitors in this particular circuit. If we write the denominator in terms first of a ratio of two polynomials, and then in terms of the standard form involving resonant frequencies and Q factor, we'll first notice that the numerator is the same as the term in j omega in the denominator. So in the standard form in terms of resonant frequency, that would give us just 1 plus j omega over q omega naught. That's the term that should be on the numerator as well, because it's the coefficient of j omega. And then we'd get j omega all squared over omega naught squared as usual. First thing we want to know is what is the maximum value of this gain here? Well, that we can do by working out what the amplitude of the frequency response is. And the amplitude of the frequency response is the amplitude of the numerator, omega over q omega naught, divided by the amplitude of the denominator. And we can apply Pythagoras' theorem here. We just take the square of the real part and the square of the imaginary part and add them together. And that will give us the square of the magnitude of the denominator. Here that would give 1 minus omega squared over omega naught squared. That's the real part of this, all squared, plus omega squared over q squared omega naught squared. That's the square of the imaginary part of this, and that is the square of the magnitude of the denominator, so we'd have to take the square root of all of that if we wanted to get an expression for the amplitude gain. What I'm going to do next is square everything. So I'm going to say, let's have a look at the square of the amplitude gain. That's going to be omega squared over q omega naught all squared over 1 minus this lot and then note that this is a perfect square, and so is this, and so is this. Therefore, they must all be positive. So what I've got here is an equation of the form square of the magnitude of the amplitude gain is A over B plus A, where A and B are both positive. Well, the maximum possible value of this would occur when B is 0. Because when B is 0, this evaluates to 1, A over A. For any other value of B, this is going to be less than 1, because remember, B has to be positive, or 0, because it's a perfect square. So the maximum possible value of this is going to be equal to 1, and it's equal to 1 when B is equal to 0. Well, B is equal to 0 when omega is equal to omega naught. So, maximum gain occurs when omega is equal to omega naught, and this term here is 0, and the maximum gain is, well, the square of the maximum gain is 1, which means the maximum gain has got to be 1 as well. In dB terms, it's 0 dBs. So we have this very simple and useful result that the maximum gain of one of these bandpass filters is 0 dB, and it occurs at the resonant frequency. If the Q factor is very small, then the poles will be spaced apart a long way and we'll end up with an amplitude response looking something like this. There's quite a large flat period there in between the break frequencies of the two poles, where the gain is approximately constant and around 0 dB. On the other hand, if the Q factor is very large, then we'll end up with a circuit more like this. A very sharp peak at the resonant frequency, but once again, the gain at the resonant frequency is still 0 dBs, and that's the maximum gain of our filter. Now, the other useful thing to know is the 3 dB bandwidth. That's a little bit trickier to work out, but there is a very simple result. We'll start here again with the expression for the frequency response and produce an expression for the amplitude response, which is just the modulus of this in the way that we've done before. At the 3 dB point, the amplitude gain will have dropped by a factor of 1 over root 2. So this is equal to 1 over root 2 when the frequency omega is at one of those 3 dB frequencies. At a frequency there, or there, where I am 3 dB down on the maximum. I'll call this omega 1 and omega 2. That's omega naught there, the frequency of the maximum, the resonant frequency. Squaring this expression here then just gives me that omega squared over q squared omega naught squared all over 1 minus omega squared over omega naught squared squared plus omega squared over q squared omega naught squared equals a half. If you look at this expression, you'll see that this again is in this form A over B plus A, as we've noted before. And the only way that A over B plus A can be equal to a half is if B is equal to A. This term and this term are equal. Then I would get a half. So I can say that at my 3 dB frequencies, omega 1 and omega 2, I must have that 1 minus omega squared over omega naught squared all squared must be equal to this term. Now, both sides of this expression are perfect squares, so I can simplify by just taking the square root. It's not quite as simple as that, because I have to be aware that I don't know whether I want the positive or the negative square root yet. So I'll just leave that in for now. This could be either plus or minus omega over q omega naught. Now, if I multiply up by q omega naught squared, just to make this a little bit neater to write, that would give me q omega naught squared minus q times omega squared is equal to plus or minus of omega times omega naught. And rearranging this, I can see that what I have here is a quadratic expression in omega. I've actually got q omega squared plus or minus omega times omega naught minus q of omega naught squared is equal to 0. And I can solve that quadratic equation using the standard quadratic equation formula. It would give me that omega, which is going to be one of my two 3dB points here, omega 1 or omega 2, is equal to minus b. Well, we don't know whether b is plus or minus yet, so we'll leave those in. Plus or minus square root of b squared. Well, b squared is going to be... Actually, you know, it doesn't matter. I could just leave this term as stuff all over 2a. 2a is 2q. The reason this doesn't matter is because what I'm interested in is the difference between these two frequencies rather than the two frequencies themselves. And whereas I don't really mind what the exact value of this stuff is, as long as I know one thing about it, I can work out what the difference between these two frequencies is. And the important thing to know about this stuff is that it's bigger than omega naught. This stuff here is actually b squared, which will be omega naught squared, minus 4 times a times c. Well, c is minus q omega naught, so that's going to be plus 4 omega naught squared q, and there's another q coming from here. The point about this is that it's always bigger than omega naught squared, which means the square root of it is always going to be bigger than omega naught. So this term here is bigger than this term here. Now, I've got a total of 4 different roots of this equation here, and 2 of those roots are going to be positive frequencies, and 2 of those roots are going to be negative frequencies. I'm only interested in the positive frequencies. So I want the 2 of these 4 different values which are positive. Well, we know that this term is bigger than this term, so the 2 values of omega 2 and omega 1 that I'm interested in, omega 2 is going to be this term, the square root of stuff over 2q, plus omega naught over 2q. And this frequency here, my omega 1, the smaller of the 2 positive roots, that's going to be the square root of stuff over 2q minus omega naught over 2q. This bigger term minus this term. Now, I can't work out the individual frequencies without working out the stuff, but I can work out the difference between them. Because if I just wanted to know what omega 2 minus omega 1 was, I could just take this minus this. These terms in stuff would cancel out. I would just get this term minus this term, but that would be 2 omega naught over 2q. In other words, omega 2 minus omega 1 is just omega naught over q, because the 2's cancel. But omega 2 and omega 1 are the 2 frequencies which are 3 dB down on the maximum. So, this difference, omega 2 minus omega 1, is the 3 dB bandwidth. Gives us this very elegant, simple formula that the 3 dB bandwidth of a second-order bandpass filter is just the resonant frequency divided by the Q factor. Okay, those are the important results for the bandpass filter. Next time, we'll have a look at the high-pass filter.